So, hello class, continuation of our discussion. So, we have this integral test, one of the tests in convergence series test. So, as for the definition, it connects the behavior of our series with an improper integral. Okay, if the term of this series, the summation of a sub n, corresponds to a continuous positive and decreasing function f of x for x is greater than or equal to n, then the convergence of the integral, which is the integral from n to positive infinity f of x dx, determines the convergence of the series. So in short, we have this condition. So if the integral converges, so does the series. Okay, it also converges, and vice versa. So if the integral diverges, so the series also diverges. Okay, it is useful when the series can be expressed as a function that is easy to integrate and analyze. So what happened here is that we given the series, we express it into function and integrate it. So make sure that we are integrating a simple function, so that it is not hard for you to integrate it. Okay, so let's have an example. So we have the series. Okay, the summation from n equals 2 up to positive infinity of 1 over n times ln of n. Okay, so if we're going to convert it into function, so this becomes f of x equals 1 over x of ln of x. Okay, so take note. Okay, if we're going to integrate this, so if we have this, the integral from 0 up to positive infinity of f of x dx. Okay, if we're going to integrate this improper integral, we must use limit. Okay, limit as t approaches infinity of the integral from 0, okay, up to t of f of x dx. Okay, we must use limit if we're integrating improper integral. Okay, if we're dealing with improper integral. So okay, so using this general formula, okay, let's say it says general formula. So we have the integral. So we have the limit. Let me write. So we have the integral from 0 up to positive infinity of 1 over x ln of x dx equals the limit as t approaches positive infinity of the integral from 0. Okay, wait. So our limit here is 2. Our lower limit is 2. It should be 2 here and also 2 here. From 2 up to positive infinity of f of x dx. Okay, so that is the correction. Okay, so at this point, okay, if we're going to evaluate this part, okay, so let's evaluate the inner expression. So let's evaluate this one. Okay, so we have the integral from 2 up to positive infinity. Okay, it should be ln of x dx here. Sorry, it should be 1 over x times ln of x dx. Okay. So we have 1 over x times ln of x dx. Okay. So use substitution. Okay. So let u. Okay. So let u equals okay, ln of x. Okay, so if we're going to integrate it, so we have du equals 1 over x dx. Okay, so next, so we have okay, so we have 1 over u du. Okay, so further, let's further integrate this. So we have 1 over u, okay, integral of that. So yeah, that is ln of absolute u. Okay, and don't forget the evaluation. So from 2 up to positive infinity. Okay, next, so if we're going to evaluate this, so we must use the limit. Okay, the limit as t approaches positive infinity. Okay, so we have ln of t. Okay, so originally our u is equal to which is this one, is equal to ln of x, right? This one, ln of x. So we just simply substitute u here. Okay, and then instead of having x, so it is replaced by t. Next, minus ln of of 2. Okay, so the answer here, so we have it is equal to so basically this term, if we're going to evaluate this, so the answer is infinity. Okay, and if we're going to evaluate this, the answer is what? So we have ln of 2. The answer is negative 0.366 or something like that, 5. Okay, so as the value of infinity, okay, as the value of t gets larger, no, so this volume negative 0.3665 can be disregarded. Okay, so in other words, the answer here is infinity. Okay, and since the answer is infinity, okay, therefore the series diverges. Okay, so that's how you solve for series. Okay, that's how you do the integral test in order to identify if your series is a convergent or divergent. Okay.